All right, today we're pulling back the curtain on the invisible architecture that runs our entire digital world. We're going to look at the actual blueprints, from the massive network that is the internet, all the way down to the Wi-Fi in your office. Let's dive in.
I mean, it really does feel like magic, doesn't it? You click send on an email and poof, it's halfway around the world in the blink of an eye. But it's not magic. It's actually an incredibly complex and beautiful system of interconnected networks. And to really get how it works, we've got to start by looking at the different scales involved.
So first up, the network universe. We're going to map our digital world. The best way to think about this is like starting with Google Earth, seeing the whole planet. And then we're going to zoom all the way in, past the country, past the city, right down to your individual street. Okay, let's start with the one you know and use every single day, the local area network, or what everybody just calls a LAN. Yep, this is your home Wi-Fi network. It's a network at your school or your office. It's just a small, private group of connected devices in one location, all under one roof, basically. Now, let's zoom out one level. We've got the Metropolitan Area Network, or MAN. And just like the name suggests, its whole job is to connect a bunch of different LANs all across a city. So if a big company has an office downtown and another one in the suburbs, they'd use a MAN to link them together. It's like the city's entire road system connecting all the little neighborhoods. And zooming out to the max, we have the Wide Area Network, or WAN. This is the big one. This is the Internet's superhighway system. A WAN is what connects networks across huge geographic areas. We're talking across states, across countries, and even between continents. And the biggest WAN of them all? Well, that's the Internet itself. So let's put them side by side for a second. LAN versus WAN. What's the real difference? Well, the road analogy holds up perfectly. Your LAN is your local neighborhood. It's small, it's private, you own it, and it's usually super fast. A WAN is the public interstate highway system. It covers a massive area, it relies on public infrastructure, and data travels a bit slower just because it has so much farther to go. Okay, let's switch gears and look inside a specific organization. You've probably heard the term intranet. Think of it as a company's own private, walled-off version of the internet. It's a website that's only accessible to employees, and it's where they put all the internal stuff. HR forms, company announcements, that sort of thing. But what happens when that company needs to give an outsider, like a supplier or a key partner, access to some of that private information? Well, that's where an extranet comes into play. It's like giving that partner a special guest keycard. They can't wander around the whole building, but they can access a few specific pre-approved rooms. It's a secure window into the company's private network. All right, part 2, digital blueprints, the architecture of connection. So we've talked about the different scales of networks. Now let's zoom way back in to the LAN level. How are the individual computers, printers, and servers actually physically connected to each other? This layout is called the physical topology, and it's literally the blueprint for the network. Now, one of the earliest ways they did this was with a bus topology. It's pretty simple. You just have one long main cable, the bus, and every single device just plugs right into it. It was cheap and really easy to set up, but it had one massive critical flaw. If that main cable broke anywhere, the entire network went down. Everybody, instantly. Another layout they tried was the ring topology. And again, the name pretty much says it all. All the computers are connected in a circle, a big loop. Data gets passed from one machine to the next in one direction until it reaches its destination. But just like the bus, it had a single point of failure. If any one of those connections in the ring was severed, the whole loop was broken and the network was dead. And that brings us to the design that completely took over and is still the standard in most LANs today, the star topology. This was a total game changer. Here, every single device gets its own separate cable that runs back to a central box, like a hub or a switch. Think of it like the hub of a wheel, with spokes going out to each computer. The huge advantage? If my cable gets unplugged, it only affects me. The rest of the network keeps on working just fine. That reliability is exactly why it won. Now, what if you need a network that is absolutely positively bulletproof? For that, there's the mesh topology. This is pretty wild. In a full mesh network, every single device is connected directly to every single other device. The amount of redundancy is just incredible. If one path fails, there are tons of others for the data to take. The downside, as you can probably imagine, is the sheer cost and complexity. Just think of all those cables. This is reserved for systems where failure is simply not an option. Okay, part 3, rules of the road. So we've got the physical map of the network, the topology, but just having roads isn't enough, right? You need traffic rules, stop signs, traffic lights, to keep things from being total chaos. In networking, this is where logical topologies and network architecture come in.
And this is a really important concept. The physical topology is how the wires are actually arranged. The logical topology is how the data perceives the network. It's a set of rules it follows. And here's the cool part. They don't have to be the same. You could have a network that is physically wired in a perfect star, but it might be logically acting like a bus, where every message gets broadcast to every single device. When it comes to these traffic rules, there are two main approaches. The first is called broadcast. It's basically a free-for-all. Any device can try to send data whenever it wants. It's like a room full of people all shouting at once. The other method is token passing. This is much more orderly. A special signal called a token gets passed from device to device. You are only allowed to send data if you are holding the token. It's like using a talking stick in a meeting, much more organized. So beyond just how the data moves, we also have to think about the overall power structure of the network. This is its architecture. In a peer-to-peer network, everyone is equal. My computer can share files directly with your computer, no middleman required. It's a very democratic setup. The other model, which is way more common in business, is client-server. Here you have dedicated, powerful computers called servers that store files or host websites, and all the regular computers, the clients, have to connect to them to get what they need. And in this peer-to-peer model, you can really see that direct line of communication. Each machine can talk to any other machine it needs to. There's no central point of control, no single boss telling everyone else what to do. It's a very robust and decentralized system. Okay, next up, connecting without cables. Let's talk about the wireless revolution. I mean, everything we've discussed so far has assumed we're plugging in physical wires. But these days, so many of our connections are just flying through the air. So how do all these same ideas apply to Wi-Fi?
At its most basic level, the difference is incredibly simple. Instead of sending data as electrical signals through a copper cable, a wireless LAN or WLAN sends that same data using radio waves. But it's really important to remember that your wireless router still has a physical cable plugging it into the wall, connecting it to the much larger wired network of the Internet.
Now, you've probably seen those weird numbers on your router, right? 802.11b, G, N, AC, and so on. Well, these are just the different Wi-Fi standards. Think of them like generations. Each new standard is an attempt to get faster speeds and better reliability. An older one, like 802.11b, for example, actually operated on the same frequency as most microwave ovens. So yeah, if you were downloading a file and someone went to make popcorn, your internet could literally just drop out.
So, let's bring it all home. Why does any of this matter? Well, from the giant global WANs down to your local coffee shop's Wi-Fi, from the physical wiring in the walls to the logical rules that data follows, these network blueprints are the quiet, hidden engine that runs our entire modern society. Everything from streaming a movie to working from home is only possible because of this invisible infrastructure. It really makes you think, though, doesn't it? As we keep demanding more speed and as we connect billions of new devices, our cars, our homes, everything, what will the network blueprint of the future even look like? What new architectures will we have to invent to keep up with it all? That's the question we're all trying to answer right now. Thanks so much for watching.